You may have heard in the wonderful world of the internet that you could find the speed of light using marshmallows in your microwave. Or peeps if that's how you roll. And these are the supplies that you could use. I recommend paper plates because they generate a little less heat than ceramic ones. Toothpicks for just general oral health, but also for finding the hot spots. And then a ruler for finding the distances between the hot spots. So let's check out the procedure here. If you can orient the marshmallows in the same way, extend them out to the rim of the plate, then that's just for my own OCD. You're welcome to do that. I found that cooking them about 1 minute at 30% power melted some of them, but not all of them, so that was a good balance for me. And then we want to make sure that it doesn't rotate because we want cold spots. So you may have to jimmy rig it if you don't have that setting. So here's what I had to do. Upside down Tupperware for the win. Plate on top, microwave, and we're golden. Then we want to find out, okay, where are those hot spots? You may have to poke around with the toothpicks, but once you find them, go ahead and leave the toothpick in there, and then yours might look something like this. Then we want to look for a pattern. Mine looks like Abraham Lincoln, but the other pattern is that there's 3 toothpicks in a row, and that's what we're interested in. That's the more important pattern, arguably. So then let's go ahead and label those. We then want to find the distance from the first to the third in centimeters. Mine was about 12.5 centimeters. Now why is it from the first to the third? Why not just halfway? Well, let's look more closely at that microwave. When we go from the peak of the wave to that peak, that distance there is the wavelength, lambda, or that giraffe-looking thing. You could see it in this GIF or GIF, The Last Great Mystery. And you could see it, all those red spots, those are all the cold spots. But then the hot spots, number 1, number 2, number 3, we got to go from the first to the third to find that wavelength. So there we go. Now, if you've done this, you're about 90% of the way done with the experiment. That's the main data point that we needed. So let's go ahead and look at the relationship here between velocity, frequency, and wavelength. If you multiply the frequency times the wavelength, that'll give you the speed of the wave or its velocity. Now we know the wavelength, we just need to convert it to meters. So let's go ahead and move that decimal 2 places to the left. That'll give us 0.125 meters. That value is what we could replace that lambda with there on the bottom right. Let's go ahead and do that. Okay. Next, we need the frequency of the microwave, and that's going to be in megahertz. But that's on the back of the microwave. And once you find that unit, that's what that value is. 2450 megahertz. So let's go ahead and write that down here. Now mega means it's times a million. So we then need to multiply that times a million, and that'll give us this value. That's the one that we're going to multiply by the wavelength there. So we're ready to go. But what does that value represent? Well, that's how many times the wave bounces up and down each second. So 2.4 billion times it's bouncing up and down like this every second. Unbelievable. Okay, let's get that last multiplication there. Okay, frequency times wavelength. Drum roll, we get 306 million meters per second and some change. Very close to the actual value of the speed of light, which is that. In fact, there's only a 2% difference between ours and theirs. When I did this with my physics classes, one class average was 298. Another class average was 301. So yeah, incredibly powerful. Okay, feel free to post what values you get. And of course, we'll see you in the next video. Toodles.